So, welcome everyone to the second talk for today, wherever you are located. This talk is our research talk given by Evgeni Dimitrov, who is a postdoc in Columbia University and at Columbia right now physically. We'll be talking about characterization of Gibbsian line ensembles. Go ahead.
Thank you very much for the introduction and for the invitation. It's certainly a great pleasure to be giving this talk. So today I will discuss a couple of recent results that characterize Gibbsian line ensembles by the distribution of their top curve. And so I'll start by kind of formulating a zero temperature version of the problem. So there the objects are called Brownian Gibbsian line ensembles. So I'll tell you what these things are. I'll give you a few examples of these objects, and then I'll formulate a certain characterization theorem for them. And then I'll kind of formulate a positive temperature version of these stories where the objects are now called H Brownian Gibbsian line ensembles. And then at the end, I'll discuss how these characterization results fit into a sort of larger framework that can be used to establish KP's universality for line ensembles. So first of all, what is a line ensemble? So a sigma indexed line ensemble on an interval lambda is just a collection of random continuous functions. So we denote this collection by this curly L, and this collection contains random continuous functions denoted by Li, where I ranges over your index at capital sigma. Now for the purposes of this talk, capital sigma is going to be a set of consecutive integers starting from 1, which could be either finite or it could be infinite. And so in plain words, a line ensemble is just a finite or countably infinite collection of random functions on the same probability space. And so as a simple example, we can take capital sigma to be the set 1, 2, 3, lambda to be the unit interval. And then if you take 3 independent standard Brownian motions, that's an example of a line ensemble with 3 curves or 3 lines. And so it kind of looks like this. And sometimes I'll kind of refer to this as a continuous line ensemble, to sort of emphasize the fact that the underlying path measure is given by Brownian motion or Brownian bridge. And later on, I'll kind of introduce some discrete versions of line ensembles. So line ensembles comes with many different types of Gibbs properties, and I'll kind of formulate one of the simpler ones, which is called the partial Brownian Gibbs property. So we say that the line ensemble has this property if it satisfies 2 conditions. So the first condition is very simple. What you want is that your curves in your ensemble, you want them to be strictly ordered. So that the first curve L1 is always strictly above L2, which is strictly above L3, and so on. So if you kind of draw them like here in the picture, they have to have this type of ordering. And then the second condition, which is kind of the essence of this Gibbs property, is that you want the distribution of these curves to locally look like avoiding Brownian bridges. So one way to think about the second condition is that you want the law of your ensemble to be invariant with respect to the following resampling procedure. So you start by sampling your line ensemble, and you plot it on this picture like this, and you fix 2 deterministic times, little a and little b, inside of your interval line. So this is the first stage. In the next stage, what you're going to do is you're going to fix a little number k, which is less than the total number of lines, and you're going to erase the top k curves of this ensemble between these 2 times a and b. That gives you a picture like this. So in the third stage, what you're going to do is you're going to fill in the picture. And how do you do that? You just sample independent Brownian bridges between the red dots that are independent, except that they have been conditioned to avoid each other and also avoid the k plus first curve here. So you sample these new bridges and you fill in the gap. So this procedure starts from some random line ensemble and produces a new random line ensemble. And the essence of the Gibbs property is that the law stays invariant. So it hasn't changed when you apply this procedure. Now the word partial in this definition has to do with the special role that is played by the bottommost curve Ln. So it plays the role of a bottom boundary in your ensemble. So it's not allowed to be resampled. It can be deterministic, it can be random, it can be whatever you want. But it doesn't necessarily enjoy this resampling invariance. However, if the number of paths is infinite, meaning you don't have a bottommost line, or you have finitely many curves, but the bottom one also can be resampled, then you just drop the word partial, and you refer to this as the Brownian Gibbs property, and this is a term that was coined by Corwin and Hammond. So in this slide, I'll give you kind of some examples of objects that satisfy the Brownian Gibbs property from the previous slide. And the first one is kind of almost tautological. So here what you can do to construct an ensemble that has this property is that you can kind of fix, let's say, some interval, let's say 0, 1, and fix some deterministic function little f, and then just sample n-1 Brownian bridges between some deterministic or random endpoints that are, again, independent but conditioned to avoid each other, and also this the graph of this function. So that's an example of a Brownian Gibbsian line ensemble. Now, a more complicated example is given by Dyson-Brownian motion. And so Dyson-Brownian motion is just a collection of n standard Brownian motions that have been appropriately conditioned to avoid each other for all positive time. So all of them start at the origin, and then they evolve for positive time, and then you need to kind of condition appropriately on them never crossing. And this is also an example of a line ensemble that has this, this Gibbs property. And the third example that I'll mention is given by what's called the parabolic airy line ensemble. And this is one of the universal scaling limits in the KP's universality class. The way that this object arises is through an edge scaling limit of Dyson-Brownian motion. So you start your Dyson-Brownian motion with n paths, and then you let n tend to infinity. And in a suitable window at the edge of this line ensemble, you will obtain in the limit as n tends to infinity an infinite line ensemble. So this parabolic airy line ensemble will have infinitely many curves, and they'll also enjoy the same type of Brownian Gibbs property. Okay, so these are just some examples of objects that satisfy this, this property. Now, the question that we want to understand is how much information do you need to describe a Gibbsian line ensemble? And to motivate this question, I'll kind of discuss an example that I like to call the princess and the pea. So the setup is as follows. So you have two beds, and one of them has a perfectly flat base, and the other one has an almost perfect flat base, except that it has a small aberration somewhere in the middle, aka the pea. Now you start piling a bunch of matrices on top of the two beds, and you can put different number of matrices on the different beds. And the endpoints of these matrices, they can be deterministic, they can be random, they can be whatever you want. The only thing you demand is that the law of these matrices should be that of avoiding Brownian bridges between the red dots that in this side need to avoid each other and also the base of the bed, and here they need to avoid the base and the P. Now a keen observer, aka the princess, observes the top curves of these two ensembles. So she sits on both of the beds, but she only interacts with the top mattress. She doesn't feel any of the ones below it, but she's very sensitive. By simply sitting on the two beds, she can determine everything there is to know about the laws of these two curves. And then the question is, based on the information that is encoded in this top curve, can the princess distinguish between these two beds? That is, can the princess feel the P? And the answer is yes. And in fact, she can determine much more than this. By simply observing the top curve of this ensemble, she can determine the entire joint law of all the curves together with the base. So in particular, she can say whether there is or there isn't a P. So this is a theorem. It's a result by myself and Konstantin Matietsky from last year. So the statement is as follows. So suppose we have two line ensembles L1 and L2 that both enjoy this partial Brownian Gibbs property that I discussed. And suppose further that the top curve of the first ensemble has the same finite dimensional distributions as the top curve of the second ensemble. Then in fact, the full ensemble's laws need to match. So in plain words, what the theorem says is that a Brownian Gibbsian line ensemble is completely characterized by its top curve distribution. Now I won't be going into the proof, but I'll mention that the proof is non-constructive, meaning that even if you have a Gibbsian line ensemble, you have nice formulas for the top curve distribution and you give them to me, I can tell you there is a unique possible law that the second curve of this ensemble can take, but I cannot give you back any nice formulas for the second curve. So in this sense, the proof is kind of a uniqueness proof rather than a constructive one. And the last thing that I'll mention about the result is that kind of as an immediate corollary, it pinpoints the parabolic airy line ensemble that I mentioned before as the unique line ensemble that simultaneously satisfies the Brownian Gibbs property and also has the correct top curve distribution, which in this for this model is called the parabolic airy process. It's again one of these universal scaling limits in the KP's universality class. It's just the usual airy process, which is stationary minus a parabola, so that kind of globally it looks like an inverted parabola. So maybe this is a good place to pause and see if there's any questions. Okay, so the next thing that I want to do is I want to formulate kind of a positive temperature analog of this result. But in order to do this, I need to formulate a more general type of Gibbs property. So this is what is kind of defined in this slide. It's called the H Brownian Gibbs property. So we say that the line ensemble satisfies this property if the law of any k consecutively labeled curves in your ensemble is basically the law of k independent bridges, except that their distribution has been reweighed by the following Radon-Nikodym derivative. Now this expression is not, it looks like a complicated function, but it's not. So it's kind of exponential of minus the sum of integrals of h of differences of certain expressions. So let's try to digest what it means. So first of all, the global behavior or the local behavior of your ensemble is that of independent bridges, except that these bridges have an interaction that is reflected in their distribution through this kind of energetic penalization term that is inside of the Radon-Nikodym derivative. Now this derivative depends entirely on this function capital H that I like to call an interaction Hamiltonian. And the argument of this, this Hamiltonian is the difference of two consecutively labeled curves. So the fact that the indices of these two curves are adjacent means that only curves that are next to each other in terms of index talk to each other. So curves that are indexed 2 or more away from each other don't communicate. And so the interaction is local in the index of the curves. The other thing to observe here is that you have that the argument of these two functions is the same, meaning that the interaction is also spatially local. So one way to kind of think about this Radon-Nikodym derivative is that it's basically e to the minus the sum. Of course, okay, here the argument is continuous, so the sum becomes an integral, but it's basically e to the minus the sum of local interactions between local in space and in index curves. And this is supposed to be some sort of a general way to formulate such a local interaction. Now, to relate this to something that we've seen before, there is kind of a simple choice for H that brings us to the Brownian Gibbs property that we discussed, which is if you take H to be the function that is infinity when X is positive and 0 otherwise. So what happens to this Radon-Nikodym derivative if you pick this choice of function H? Now, if the difference here is positive, what does that mean? It means that the I plus first curve went higher than the ith curve, which means that the order of the curves is broken. And any such path configuration is going to be reweighed by e to the minus infinity. So it gets a weight of 0. So anytime the curve go out of order, they get weight 0. And so these path configurations get no chance of occurring. On the other hand, if the differences are always less than or equal to 0, meaning that the curves are ordered, then your Radon-Nikodym derivative is going to be e to the minus 0. So that's a 1. So the effect of reweighing by this Radon-Nikodym derivative is that it kills the weight of all path configurations that go out of order, and it leaves invariant the weights of path configurations that keep their order. So that's exactly the Brownian Gibbs property, basically getting uniform measure on ordered paths. Now, another natural choice for this interaction Hamiltonian is given by an exponential function. So you're looking at functions of e times to the power of a positive constant times x. So I'll explain in a moment why we denote this constant by t to the 1/3. But one way to think about this one parameter family of interaction Hamiltonians is that it interpolates between complete disorder and complete order as t ranges from 0 to infinity. So if t is equal to 0, this function becomes identically equal to 1, which means that it's a constant function. And then this Radon-Nikodym derivative is also going to be constant. Now, if you reweigh a probability measure by a constant weight, you leave the measure invariant. You don't change the distribution. So you still have that the local distribution is just that of independent bridges. And independent bridges can go out of order as they please. Now, as t tends to infinity, this function exactly converges to this one here. That is the indicator of x bigger than 0 times infinity. And so you exactly recover the usual Brownian Gibbs property in the limit as t tends to infinity, which is complete ordering of the paths. So this is a one parameter family that kind of interpolates between complete disorder and complete order. Now, a remarkable result that is due to Corwin and Hammond is that they were able to construct a line ensemble that satisfies this H Brownian Gibbs property with this interaction Hamiltonian. And it is what is called the KPZ line ensemble. And it is also one of the universal scaling limits. It's kind of the weak noise scaling limit in the KPZ universality class. And it kind of looks like this. So here I kind of drawn you a picture for it. So I won't give you a formal definition, but I'll try to explain what are some of the features of this ensemble. So first of all, it's a positive temperature model, meaning that the paths are no longer strictly ordered. So they can go out of order, as you can see on the picture here. Now the paths are allowed to go out of order, but they don't like to do this because every time they go out of order, that comes at an exponential energetic cost. So even though kind of entropy-wise, they're every once in a while they do go out of order, you know, the energy of such path configuration is actually pretty small, and so if they go out of order, they tend to go back in order quickly. Another thing that I'll mention is that similarly to the parabolic area line ensemble, the top curve in this ensemble plays a distinguished role in the KPZ universality class. The top curve, or the lowest index curve, L1, is nothing but the Hopf-Kohl solution of the KPZ equation started from narrow wedge initial data. And so this is why we have this interaction being t to the 1/3, so that the top curve is exactly the time t solution to the KPZ equation. Okay, so in the previous slide, I kind of formulated the statement that characterizes the parabolic area line ensemble by its top curve. So it's natural to seek a similar type of result for the KPZ line ensemble, which would be a kind of a positive temperature analog. So that's the content of the following theorem. So the statement is similar to the one we had before. So suppose you have two line ensembles, L1 and L2, and they both satisfy this H Brownian Gibbs property. And also suppose that the top curve distribution has the same finite, of the first ensemble has the same finite dimensional distributions as the top curve of the second ensemble. Then you can conclude that the laws of the full ensembles need to match. Now that is true if you have a few technical assumptions on the interaction Hamiltonian H. So one of them is that H needs to be a convex function. So that's simple enough. Now the second statement here looks complicated, but what it essentially says is that you want your capital H to grow at infinity, essentially like an exponential function with a fixed parameter lambda. So for example, if H is identically equal to e to the lambda x, this ratio is going to exactly cancel with this thing for all possible values of x and y. And this is a certain relaxation of the assumption that you can make while still kind of using the same arguments. So you can handle slightly more general than just exponential interaction Hamiltonians in this way. So again, in plain words, what the theorem says is that an H Brownian Gibbsian line ensemble is completely characterized by its top curve distribution. And specifically, it pinpoints the KPZ line ensemble as the unique Gibbsian line ensemble with this interaction Hamiltonian that has the narrow wedge solution to the KPZ equation. Okay, so these are the two results. Again, I'll pause to see if there's any questions. Okay, so we have two kind of characterization results for Gibbsian line ensembles. So natural question is, are they useful for anything? You know, why do we care about having such results? And I'll kind of give two lines of motivation for why you might be interested in these types of statements, and focusing for the rest of the talk on the second one. Now, the first one is, there is a general interest in understanding the structure of the space of measures on Gibbsian line ensembles. Okay, so you want to have kind of a nice description of, kind of compact description of what is a kind of enough information to encode the law of a Gibbsian line ensemble. So it's not difficult to see that the space of such measures is a convex set, and one is generally interested in finding some sort of a description of the extreme points of this set. Now, of course, the previous theorems don't really say much in this direction, but they're kind of this type of flavor. We're trying to get a sense of, you know, what do we need to control in order to basically pinpoint these objects. And there's kind of beautiful conjectures that you can find in the paper of Corwin and Hammond that are attributed to Andrei Okonkov and Scott Sheffield that kind of characterize the area line ensemble as the unique ergodic stationary line ensemble that when shifted up by a parabola enjoys the Brownian Gibbs property. Now, the second sort of motivation for these results, which is the one that I'll discuss more, is that these theorems, they pave a route toward, towards establishing KP's universality for line ensembles. So the general type of question that I have been thinking of in different contexts is essentially the statement of under what conditions can you deduce that the sequence of discrete line ensembles converges to the parabolic airy line ensemble. And I'll be interested in a sort of uniform convergence, meaning in the topology of uniform convergence over compact sets in this space. And so to kind of explain what is a discrete line ensemble, again, they come in many different flavors. So I kind of formulate it with a picture, at least one of them, and then that naturally kind of arises in the basic statistical mechanical model of lozenge tilings in the triangular array. What I've drawn here is a certain polygonal domain in the triangular array, and I'm going to consider all possible coverings of this domain by three types of tiles. These are sometimes called lozenges, that are basically the three possible ways that you can glue two triangles in this array along a common side. Okay, so this is one possible way to tile this region. There's finitely many ways to do this. And we're going to put the uniform measure on all possible tilings of this domain. And so this is hopefully for people in this audience, a familiar picture. Now, there is a natural way to obtain a line ensemble from this picture, which is you start from your tiling and you perform a simple affine transformation that brings you down here. And at this point, what you can do is you can draw black segments that connect the midpoints of the blue and the red parallelograms in this picture. And in this way, you obtain a collection of upright black paths. Now, for different tilings, you get different upright paths. And so the uniform measure on the possible tilings induces a probability measure on random upright paths. And at this point, you can erase the tiling if you want and just keep the paths intact. And it is not too difficult to convince yourself that the uniform measure on all possible tilings induces the uniform measure on all upright paths that all start at 0, and in this case, all end at 3, and are uniform kind of avoiding paths, which is essentially the law of 3 avoiding Bernoulli random walkers that are conditioned to avoid each other, but also avoid the bottom boundary of this domain. Okay, so hopefully it's clear from the picture that how the correspondence occurs, and that this is indeed kind of a discrete analog of the Brownian Gibbsian line ensemble that I had before, where the only thing that changed is that I replaced the Brownian motions that underlying that path measure with Bernoulli random walks instead, which are discrete objects. Okay, so here's a kind of a few other types of situations of kind of, again, statistical mechanics model that naturally carry a structure of a line ensemble. So this is domino tilings of the Aztec diamond. This is the multi-layer polynuclear growth model. And this is, again, the lozenge tilings for slightly different domains. I kind of took this picture from a paper by Leo. It's, again, the same type of lozenge tilings for what are sometimes called sawtooth domains. So all of these models naturally carry a structure of a line ensemble. And in fact, for all of these models, it is known that the finite dimensional distributions of these ensembles converge to the parabolic airy line ensemble. Now, the reason this is known for these models is because they are special. They are what are called determinantal point processes, or they have the structure of a determinantal point process with a kernel that is suitable for asymptotic analysis. So I'm not going to assume that people know what the determinantal point process is, but the key point is that these models have a very enhanced underlying algebraic structure. And from kind of an asymptotic analysis point of view, the key point is that the correlation functions of these models can be expressed as determinants of a function of just two variables, which is called the correlation kernel. So if you have nice formulas for this correlation kernel that are suitable for asymptotics, and you can show that these kernels converge to what's called the airy kernel, which is the kernel underlying the finite dimension distributions of this line ensemble, then this type of convergence is enough to conclude finite dimensional convergence. Now, I'm being a little bit reductive. One needs to prove sufficiently strong type of convergence, but essentially that is the point. Now, having a determinantal point process structure is a special property. It doesn't hold even for kind of well-studied integrable models, and let alone for generic models. So kind of the ideas that establish these types of results for these models that I have here on this slide do not extend to the general setting. Yet we're still interested in establishing, at least if one is interested in proving KP's universality in some sort of generality, we're still interested in establishing these types of results. And so in order to answer this type of question, so I've been sort of thinking over the last year and a half about developing a certain type of framework. So let me explain to you what is the framework. So if you have a sequence of discrete line ensembles and you want to show that they converge to the parabolic airy line ensemble, and again, we're going to be ambitious. We're not just going to be satisfied with finite dimensional convergence. We're going to ask for more. We're going to ask for some sort of uniform convergence. We need to establish two things. So the first statement is kind of a qualitative statement. We're going to be, we're going to want to show first that these ensembles form a tight sequence, not necessarily convergent, but at least tight, so that you at least know you have some subsequential limits. And moreover, we're going to demand that all subsequential limits satisfy the Brownian Gibbs property. Now these things, this type of statement is kind of likely to be fairly generalizable. The reason being that, for example, if you have some sort of avoiding Bernoulli random walkers, and you imagine that you know that this sequence of line ensembles is tight, then in the limit, the Bernoulli Gibbs property, the fact that the local distribution of those ensembles is that of avoiding Bernoulli random walks, in the limit should converge to the statement that the limiting object should have local distribution given by avoiding Brownian motions instead. So you want, again, to have some sort of a qualitative control of your sequence of line ensembles, and to say something qualitative about the limit. Now, the second point is you still need to control some sort of a quantitative aspect of your ensembles. Namely, you want to show that the top curve of your discrete line ensemble converge in the finite dimensional sense to the parabolic airy process, which I remind you is the top curve of the parabolic airy line ensemble, this universal scaling. Now, suppose you have established these two statements. How does the first theorem that I mentioned basically tell you that you're done? So if you have a sequence Ln and you know that it's tight, then you know that you have subsequential limit. Now pick one of those subsequential limits. What do you know about it? So the first condition here is telling you that you know that it satisfies the Brownian Gibbs property. And then the second condition here is telling you that any subsequential limit has to have the top curve being equal to the parabolic airy process. Now the first theorem that I mentioned says that there is a unique possible object that satisfies both of these conditions, namely the parabolic airy line ensemble. So you have a tight sequence and only one possible candidate to be the limit. So that implies convergence to that candidate. Okay, so the benefit of this framework is that it reduces the amount of quantitative information that you need to control from the full ensemble to only the top curve. Okay, so you don't care if you have formulas for the second, third, or other curves. You only care if you have some sort of precise control for the top one. That's still a lot for many models, but it's at least definitely less. And so that's why there is some hope of this being generalizable as opposed to the determinantal formulas that I mentioned in the previous slide. So let me mention kind of maybe a couple of applications of this type of framework. So the first one is kind of a cute result that we worked on last summer. So there was a Columbia-run REU program. So these 5 people were undergraduate students at Columbia, and Wei Tao Zhu is she's a 3rd-year graduate student at Columbia. And so what we were able to do is to show that if you have a sequence of n avoiding Bernoulli random walkers, so you assume that they start from whatever you want, random or deterministic initial configuration, and they terminate at some random or deterministic configuration, and maybe they're conditioned to stay above some function. And you assume that under suitable scaling, the top curve converges in the finite dimensional sense to the parabolic airy process, then you can conclude that the full ensemble needs to converge in this uniform sense. So what the theorem is essentially saying is that the Gibbs property that avoiding Bernoulli random walkers enjoy improves the finite dimensional convergence of the top curve in two ways. First of all, it improves it from finite dimensional to uniform. And secondly, it improves it from the top curve to the full ensemble. So there's kind of a two-level improvement going on here. So again, I won't really be going into the proof, but I'll mention that in essence, in order to establish tightness, which is the essential thing that you need, we don't even need actually finite dimensional conversion. So this result is only required to apply theorem 1 to classify the limiting object. But to show tightness, we only need 1 point tightness of the top curve together with some sort of a global parabolic behavior. So for example, if you know that the top curve 1 point marginals converge to Tracy Whittem, that's enough to conclude that the full ensemble is tight. And moreover, that all subsequential limits satisfy this Brownian Gibbs property. Another thing that I'll mention is that one of the authors, Christian Serio, in his senior thesis this year, extends this result by replacing Bernoulli jumps with kind of general classes of jumps. So it's not whatever you want. So basically, he can handle kind of jumps that are integers on connected intervals of support and have a log concave distribution or something like that. So for example, what he can definitely handle are things like geometric jumps or Poisson jumps or uniform on some integer interval jumps. So one can generalize the results of this theorem to more general jumps as well. Okay, so going back to the framework, I'll just mention again a couple of additional applications. So the models that I'm interested in applying this framework to come from the McDonald processes that were introduced by Borden and Corwin. There's kind of two models that I have been sort of thinking about. The first one is coming from what they're called the Whole-Littlewood processes. And there's a kind of a nice plane partition model, random plane partition model that arises there that has the structure of a line ensemble. So let me see if there's a question in chat. Okay. Well, it was not easy. It is not easy to split work seven ways. I'll tell you that. Anyways, maybe I can say more at the end if you're interested. But right, so as I was explaining, so one of the models is coming from Whole-Littlewood plane partitions, and the other one is coming from the log gamma polymer, which also carries the structure of a line ensemble through the geometric RSK correspondence. Now, both of these models are non-determinantal. They're kind of positive temperature models. And the framework hasn't been, completely worked out. So that's still work under progress, but there has been some partial progress for the Whole-Littlewood case in these two papers and for the log gamma polymer in these two recent results. But the last thing that I'll mention is that this framework, you can replace the parabolic area line ensemble with the KPZ line ensemble and have an analogous type of framework. And at least for the log gamma polymer, it appears that both of these points are basically established in the PhD thesis by Xuan Wu. So it should be the case that using her results, one can verify the uniform convergence of the log gamma polymer under weak scaling to the KPZ ensemble. And again, this type of framework kind of should work in general for other Gibbsian line ensembles. So I've mentioned the two, but there are others. There's things called Airy Wanderers processes and other possible kind of Gibbsian line ensembles that one can sort of think about and try to show convergence to. Okay, so I think that's all I wanted to say. Thank you very much for your attention. I'll take questions if people have.